Okay, so we're going to continue with our study of Gauss's law, and now we're going to look um, at conductors or metals and learn a few things about them using Gauss's law. So we're going to start off with a simple but really important proposition, and that is that if you have a piece of conductor, a piece of, say, metal, and it's in equilibrium, then the electric field is going to be zero inside the interior bulk of the metal. Let's prove that in a simple way. Let's imagine we have parallel plates. Here's a positive plate, here's a negative plate. And so there's going to be an electric field, let's call it an external field, inside these plates that is going to go from the positive, away from the positive, and towards the negative. So there's that external field. Now, let's take a piece of conductor, and let's imagine the conductor is neutral. So it's got as many positives as it does negatives, right? But in a conductor, of course, these negatives are free to move around. So if you take that conductor, and if you plunk it down inside these parallel plates, then because of that field, the electric field, minuses are going to move. Basically, they're going to be attracted to this positive plate. So they're going to start to shift a little bit, right? They'll kind of move over like this. Now, that means that inside this conductor, you now have a more negative side and a more positive side. Well, that's going to correspond to there being a field inside this conductor. And we'll call that the internal field. It's the field that's due to those shifted electrons. Now that field is going to grow until it balances the external field for the following reason. If you're a minus sign and you're inside this conductor, and if this field is still smaller than this one, that means there's still a resultant field which is to the right. And if there's a resultant field to the right, the electrons are going to keep moving to the left. And they'll move to the left until this piece of conductor is so polarized that this internal field balances the external. Because when that happens, there's no net field, and therefore no more force on the charges, and therefore these free electrons won't move anymore. Well, we've exactly proved our assertion. At that point, the electric field inside the metal is zero, because the internal and external cancel each other out and give a resultant of zero. Okay, so let's just compare and contrast, though. This is only true for a metal. So if we come along and if we apply an external field to a piece of metal, then the minus signs are going to move opposite to the field, because this positives go in the direction of the field, so minuses go opposite to the field. That's going to leave this side of the metal as positive, create an internal field inside this block of metal that exactly cancels out the external field, so the net field inside is zero. Okay, so that block of metal is, we say, polarized. Now, an insulator will still polarize, but the charges are not as free to move around, so you won't get as large an internal field. So in the insulator, without the free electrons, the minuses are still going to shift, right? So let's just draw an insulator, say, covalent molecules. So the minuses are still going to shift opposite to the direction of the electric field. So you're still going to get an internal field here, but the charge motion isn't as efficient, and so the internal field is going to be a lot smaller. And the net electric field, so that says E internal, believe it or not very well written, and it's smaller than the external field, so the net field is bigger than zero, and it's going to be to the right. So the internal field partly cancels the external field, but not completely for an insulator. Whereas for a conductor, because the charges move so well, the internal field totally cancels the external field. Okay, so let's take that result one step further. Let's take a block of metal, and let's put an imaginary Gaussian interior, this block of metal. Okay, so this is like a metal cube. Our Gaussian surface is entirely inside the metal. Now, what does Gauss's law say about that Gaussian surface? Well, it says the flux of the electric field through this imaginary Gaussian is 4 pi k times the enclosed net charge. Well, we know that the electric field is entirely zero inside the metal. We just proved that earlier, right? Once it reaches equilibrium, the minuses will have shifted to create no field inside. Well, if the field is zero, then it must be that the flux is zero. And if the flux, that's this side of the equation, is zero, that means that the enclosed charge is zero by Gauss's law. Now, when we say it's zero, that doesn't mean there aren't any charges in there. It just means that the positive and negative are canceling each other out. The enclosed charge just being zero just means the minuses and positives are equal in number. There's no excess charge. Okay. So let's say we had hollowed out a solid metal ball to create a hollow metal sphere. And let's imagine that we left a tiny opening here, and so we could put, tiny charged particles in here. So let's just put a little Q here, right in the center. Okay, so that's a real charge right there in the center. So we're going to claim now that in this case, there's going to be a separation of charge in this metal object. And we're going to claim that in the following way. Okay, so here's a point charge right in the middle of this hollow metal sphere. We're going to put a Gaussian here. Now this Gaussian is entirely inside metal. Okay, so this Gaussian is entirely inside the metal. Right, because this is a concentric, a hollow metal sphere. Now, now because it's entirely inside the metal, we showed earlier that the electric field is zero, and therefore the flux will be zero. But we know that the flux is 4 pi k times the enclosed charge. So that means that the enclosed charge is zero. But the enclosed charge inside this Gaussian includes two things. It includes the point charge, which is at the center, and it includes the inner surface charge. Now, we just proved that inside a metal, there could be no excess charge. There can be excess charge on the surface. In fact, that's where any excess charge has to be. So we've got a point charge Q, and then the Q on the inner surface. Well, together those have to be zero by Gauss's law. So this proves the result that we were looking for, which is that the charge on the inner surface, that surface charge, must be the opposite of any charge placed in the middle. So if this is plus 2 microcoulombs, there must be minus 2 microcoulombs on the inside surface. We had mentioned this earlier in the course, but now using Gauss's law and this Gaussian, we can prove that result. All right, so now we'll just go back to doing some standard Gauss's law problems with occasionally appealing to our knowledge or our new understanding about conductors. So here's a classic Gauss's law problem. We're going to find the electric field outside and the electric field inside both a metal sphere, so a solid metal sphere, and a solid insulating sphere. So let's go through the metal sphere. Now, we just proved that if the metal has excess charge, none of the excess can be interior inside the metal. All of the excess charge must be on the surface. So all of Q must be on the surface, because you can't have any excess in the bulk of a metal. So that means we have a surface charge density. That's a ratio of charge to area. The area of this sphere is 4 pi r squared. Okay, now that's not essential to solve the problem, but it's worth mentioning and understanding. So the electric field outside, well, we'll use this Gaussian here. Okay, so this blue Gaussian, let's call it Gaussian A, I guess. So no, A is already taken. All right, sure, capital A. So let's apply Gauss's law then to that Gaussian. So the flux of the electric field through that imaginary Gaussian is 4 pi k times the charge enclosed. Okay, now we have proper symmetry here. The electric field in spherical symmetry will be in the radial direction, so it'll cut through this Gaussian. It'll be parallel to the outwards pointing surface vector. So that means we can drop the dot product. This Gaussian is concentric with the charged sphere. So that means that the electric field will be everywhere constant on the surface of the surface. So first we can drop the vector signs because E is parallel to dA. Next, the electric field will be uniform, so we can pull it out. Adding up dA is like finding the surface area. And the surface area of that Gaussian sphere is 4 pi times r squared. This is radius r. Okay, now that's 4 pi k times the enclosed charge. Now the charge enclosed by the Gaussian is the entire metal sphere. That is 4 pi k times q. Canceling out the 4 pi, we get kq over r squared outside. Now, if we were dealing with an insulating sphere, and we did this problem last time, okay, for an insulating sphere, Q is distributed throughout the volume. So we don't have the charge on the surface. Instead, it's spread throughout the entire body of the insulator. So that means we have a volume charge density. It'll be charge over volume. So the Q is spread out over 4/3 pi r cubed. But if we put a Gaussian on the outside, I guess maybe I'll call this Gaussian B, then when we apply Gauss's law, we're going to essentially have exactly the same conclusion we did on the other side. So there's the right symmetry for the Gaussian, so the dot product and the vectors disappear because E's parallel to dA. E's uniform, so you pull it out. Adding up dA gives you the area. The area of this Gaussian sphere B is 4 pi r squared. So you get the same answer for the electric field. And we kind of alluded to that last time because we said from the outside, any charge distribution just looks like a point charge. So this looks like a point charge Q, and so does the metal sphere, right? It also has spherical symmetry, so from the outside of the sphere, it just looks like a point charge at the origin. All right, so these were the same. What's different is when we go inside. So if we are inside this metal sphere, well, hold on, okay? We showed previously that the electric field is 0 everywhere inside the metal. So that's an easy calculation. So this is for R bigger than R. For R less than R, the electric field is 0 everywhere inside the metal. So we're done then with that calculation. For the insulator, we're not yet done, and we're going to need to set up a Gaussian here. That's Gaussian C, I guess. And let's apply Gauss's law. And having done this question already, you may recall that the challenge becomes to find the amount of enclosed charge, because this Gaussian sphere encloses some of the charge Q, but not all of it. Now, the expression on this side works out to be the same, because if you pick, this is supposed to be a spherical Gaussian will have the right symmetry. The electric field will be radially cutting through the edge, so you drop the vectors. It'll be uniform over the surface of the Gaussian, so you pull E out, and you just get E times the surface area, which is 4 pi r squared, where r is the radius of that little Gaussian sphere. Now, on the other side, 4 pi k, we ask the question, how much charge is there inside that Gaussian? Well, you'll recall in class, we used a ratio. We said the total charge over the total volume will equal the enclosed charge in the Gaussian over the volume of the Gaussian. Now, the volume of the Gaussian being 4/3 pi r cubed, little r, we arrive at a ratio. So the enclosed charge is a certain fraction or a certain multiple of Q. Canceling off the 4/3 pi's, the enclosed charge is the total charge Q times little r cubed over big R cubed, where this is the radius of the Gaussian and this is the fixed radius of the insulating sphere. So, canceling off the 4 pi's, we get KQ R over R cubed. So this was the electric field when we were outside the sphere. This is the electric field inside. Now, we actually went through this last class. It was one of the first examples we did with Gauss's law. So it's really this side that's new, the electric field for a conductor, conducting sphere. Okay, but it's worth going through the problem again just because Gauss's law is tricky and it takes a while to learn. That's our pre-lecture for today. We'll pick it up at this point in class.